Hey everybody, welcome to module number 2 and workshop number three's three-part series on tracking energy performance. We're going to continue to build on the foundation that will support our energy savings efforts in the SEM program. As a reminder, the objectives for workshop 3 are to learn different approaches for tracking energy performance and to learn how to analyze and understand energy performance results. In the first video, we focused on introducing energy tracking and KPIs. In this video, we focus on methods of tracking energy. And the final video is catered to sites that will have an energy intensity model. There are two methods the Energy Trust SEM program uses to track energy. Let's get into those now. One of the two methods is a top-down approach, which is an energy intensity model. For this method, a model is developed that can accurately predict your site's energy use. As energy savings projects are completed, the actual energy use as energy savings projects are completed, the actual energy use that comes from your electric meter should reflect by being lower than your predicted use. Predicted energy use and actual energy use are compared, and the difference is the savings. In this module, we will provide a deeper introduction into energy models, and then in the third module in the three-part series, we'll do a deep dive into how models are created and function. The second method is a bottom-up via project-based calculations. For this method of energy tracking, we utilize calculations for specific projects and an annualized sum to look at program savings. For this method, we need to understand equipment specs and operational states before and after energy efficiency projects are completed to complete calculations. Both the energy intensity model and project-based calculations have their pluses and minuses. We will provide an overview as well as a comparison of the methods later in this video. Let's dig into the energy intensity model first. Because looking at energy bills doesn't show you the whole picture, you need other ways of understanding what drives energy use at your facility on a day-to-day basis. To build an energy model, we look at things like weather, schedule, and materials to determine how they correlate with your site's energy use. Each of these has a different impact on your energy use, which is why we call them energy drivers. After looking at different energy drivers at your facility, we can determine which ones are most helpful to predict energy usage at your site. With a basic understanding of energy drivers, I'm going to explain how they fit into the overall model development process. First, we collect data. We look at all kinds of information you are able to compile. Examples include units produced per line per day, or units of each product processed, or equipment downtime. Then we establish the relationships between each data point and energy usage. From that information, we define key energy drivers, and from there, we build the model. This is the general process we use for building a model. Building an energy intensity model can be a time-consuming process. The process involves collecting and reviewing data and identifying the key variables such as energy drivers that affect energy performance. Here, we can see how the timing overlaps with the SEM program. Model development is not always smooth sailing. Sometimes in month 1 through 3, it becomes clear a model will not work due to complexities of your site or issues of access or quality of data. Another example could be that late in the engagement, large changes to schedule, processes, or new equipment confuse the model. These are examples of where we may have to transition from an energy model to project-based calculations. Now that we understand how the model is created and the associated timeline, let's see what they actually look like. Here we're going to look at an example of what an energy model looks like. This blue line shows the actual energy consumption for the baseline period. This is data collected directly from your electric meters. In this example, there are dips in energy use that happen in general on a weekly basis. This could be a facility that typically operates 6 days a week, and the low energy use are days when there is no production. The yellow line we see here is an example of predicted energy use. Given your energy drivers, this is how much energy your model predicts we will use. This is how we test the model. We look at your historical energy usage and compare it to the predicted use in the model to confirm there's a high level of accuracy. Once the model is created, we maintain it by regularly updating energy driver data and actual use. After the baseline period, we update the model and start to compare the difference between actual use and predicted use. However, the difference can be hard to see. It's not until we add a cumulative sum, or QSUM, that we can clearly see the trends. In this case, we started the QSUM when the baseline period ended and the first year SEM program began. Now down is good. As energy savings projects are completed, the actual energy use should reflect by being lower than your predicted use. Predicted energy use and actual use are compared, and the difference is the savings, or a line we call QSUM. We can see that we started out a little slowly, using more energy than we predicted. But after a few months, we got things under control and turned our trend around by implementing the energy savings actions identified. Now, we use an online energy performance platform tool we often refer to as the EPP. Some of you may have already been introduced or accessed the EPP. The Performance tab is where you upload your energy data and view performance of your energy model. Now, we consider the beginning of the SEM program the implementation period. During this time, you're establishing SEM practices, identifying and executing projects, and monitoring results. In reality, those practices are ideally just getting started and continue on. Toward the end of the SEM engagement, we'll start to look at the reporting period for sites that have energy models. Energy models utilize reporting periods. A reporting period is a specific time frame in which we look at the savings trend and then extrapolate that trend in the period to calculate annual savings. Note, the reporting periods can vary in length. So energy intensity models are robust and accurate, but they do have their limitations. If there's major process changes, if there's significant increases or decreases in production, if there's large non-SEM energy projects, there's new products, there's major schedule changes, or projects completed outside the model boundary. Now, each of these can disrupt the model. These are sometimes detected via extreme savings trends or what appears to be excessive energy use. Sometimes energy models can be adjusted to account for things like schedule changes or running new products. However, those occurrences can also invalidate an energy model. When an energy model is invalidated, or one cannot initially be developed, we use project-based calculations. I'm going to pass it over to Kevin to talk more about project-based calculations and how they're performed.
Thanks, Nick. So yeah, we've talked a bit about how to understand an energy intensity model gets used to quantify energy savings, and now let's spend some more time getting a better understanding of project-based calculations. So project-based calculations are really just a way to quantify savings at the equipment or system level, and they're often used in SEM engagements, and they're even sometimes used in parallel with energy intensity models. Project-based calculations require that we collect some information about the energy system in question before and after the change was made, so we can calculate the difference in energy use, which is essentially the savings. They may require that we take some measurements or pull trend data to accurately calculate savings. And when doing project-based calculations, it's important to consider three different factors. So the first one is the rated power. That's the amount that's shown on the motor nameplate or what's stamped on each lamp for a lighting system. We also need to consider the runtime. Essentially, we want to ask, how many hours per year does this piece of equipment operate? And again, we might be thinking about how many hours per year are we going to reduce the operation of that piece of equipment? And the last factor is the load factor. And what that signifies is just, how hard is that piece of equipment running? And I like to use an example when thinking about load factor. So let's envision a conveyor, right? Let's say that conveyor has a 5 horsepower motor on it. When that conveyor is fully loaded up with product, it's probably requiring about 5 horsepower from the electric grid. However, when that conveyor is running empty and it's just idling, maybe it's only going to pull about 2.5 horsepower from the electric grid. So in that case, the load factor when it's fully loaded up and pulling 5 horsepower is about 100%. And in the case when it's just idling and only pulling half of the rated power, we would call that about a 50% load factor. So it's really just a measure of how hard is that piece of equipment operating. Now we call these three factors the trio of energy use because they're each key components to calculating energy use and therefore energy savings. When doing project-based calculations, we need to have a reliable source for each piece of information in the trio of energy use. So let's look at a few sample projects to see what type of information we may need to collect to complete project-based calculations. Here we've got a sample list of 4 projects, and we'll just run through each one of them. So up on the top here, we've got compressed air leak repair. Let's say you're in the SEM program, you find a whole bunch of compressed air leaks, and you go about repairing those, and you repair a whole bunch of them, and it amounts to over 150,000 kilowatt hours a year of savings. Well, we could quantify that savings via a leak log. And really, on the leak log, all we're going to have is we're going to have a measurement from the ultrasonic leak detector that indicates the sound or the decibels of each leak. We'll know the pressure that that leak was at. That allows us to get the flow, the CFM of each leak. Then our engineers will collect information in your compressed air system to look at how efficient it is. And they may also ask you, hey, how often is your compressed air system pressurized so we can know the annual operating hours. With that information, we can pretty easily calculate the energy savings from repairing those compressed air leaks. For our next project is a fan speed reduction. This one's a little bit smaller at 36,000 kilowatt hours a year is the estimate here. And let's just say in this case, this is part of a fan system that's trended in a building automation system. Well, what we can do in that case, if you've got trended amps for that fan system, we can go ahead and just download that trend data. And in doing so, what we'll see is okay, whenever that fan is on, we'll see the amps are above 0. And when it's off, they're at 0. So we've pretty much got the runtime information right there. And the amp data, that essentially tells us that combination of rated power and load factor, because that's going to be used to do a simple calculation to quantify the input power for that piece of equipment. So we kind of have all the information we need right there in that trend data. Our next project is the motor runtime reduction. Let's say that's a big motor. That's a 50-horse motor. It's going to have a big impact, 85,000 kilowatt hours or so. But in this case, it's not part of a building automation system. So we can't just go and download trend data. Well, we've got another good option here. What we can do is we can go ahead and deploy a data logger to collect log data. And all the data logger is, it's just a clamp-on current transducer, which is going to go around one of the legs for the wires going into the motor. And when that motor gets turned on, it will record the amperage going through that leg. And again, just like with the trend data, by recording a time series of the amps going to that motor, we'll be able to see when it's turned on and when it's turned off. We'll also be able to see or relatively easily calculate the input power to that motor. And that's the key information that we'll need to calculate savings. Now, lastly, we've got a lighting shutdown SOP. This is shown as being the smallest project in the list. And when we have these smaller projects, we can kind of reduce our level of rigor required. And we can go based on less measured data or trended data and more on nameplate data and estimates. So in this case, maybe we're able to look and see that each lamp is 32 watts. And we can count and say that, oh, there's 100 lamps that are impacted by this shutdown SOP. And then maybe we would just ask you at the facility, how many hours a year were these lights operated before you implemented this lighting shutdown SOP? Maybe they were on all the time. They never got turned off. No one knew where the switch was. And then afterwards, they're getting turned off at 7 p.m. on a Friday and turned back on 6 a.m. on a Monday. Now, with all that information, we've got enough to fill in kind of our trio of energy use that allows us to calculate energy savings in the baseline condition before the SOP was implemented and in the post condition after the lighting shutdown SOP was implemented. So we can accurately quantify energy savings. Now, the last thing I want to say with this is is when doing project-based calculations, we typically only do the actual full calcs on a subset of completed projects. And we're going to prioritize those projects that are the most impactful, so the biggest savings, and are the most reasonable to measure. So with that, let's go ahead and let's look over at what the implementation and reporting periods look like for project-based calculations. This is a little bit different than if you have an energy intensity model. Now, if you're using project-based calculations, essentially any project that you get done during your 1 year SEM engagement period, so that's going to be, if you started in October, that'll be month 0 here. That'll be between October 1st all the way through to September 31st of the coming year. That entire SEM program year is also your implementation and reporting period. So they all kind of get just smashed into one, and any project you complete during that period of time, you will get kind of credit for the full annual savings from that project. Now, I do also want to mention that any projects you get done after the end of your reporting period, they don't just, go away into the ether. What we can do is if you enroll in another year of SEM, those will count towards your next year's program goal. If you decide not to enroll in a future year of SEM, we can connect you with your account manager and see if that project will be eligible to kind of spin off into another Energy Trust incentive program. All right, just like we did with the energy intensity model, let's take a look to see how project-based calculations show up in the energy performance platform. So when you're within the energy performance platform, if you go to the projects tab, you might see a little savings sub-tab. And what we're going to see if we look down lower here is we're going to see this purple series. And I like to think of this purple series as slowly kind of squiggling up and going over to the right. Now, the horizontal axis here is times. This is as the customer is progressing through their SEM program. And the vertical axis is energy savings. And I recognize this is really small, but we'll just kind of talk this at a high level. Now, as projects are completed, that's each of these little green boxes is a project getting completed. We'll see the purple line squiggle up just a little bit. And the amount that it goes up by, you notice it goes up in this vertical fashion, because what we're essentially doing is we are assigning the annual savings for that project to the day it was completed. Now, that's not the way the project's going to show up on your electric meter, but it's how Energy Trust does their accounting for the SEM program, and that's how your incentive would be calculated within the SEM program. Now, if you want to see, hey, how does this show up on my electric meter? We also have the cumulative savings view in the energy performance platform. It's just a little toggle. Right on that same graph, you can switch back and forth between the two views. And now what you can see is you can see how these savings would stack up on your electric meter. And you'll kind of notice as projects get completed, the savings slope increases. Because now what's happening here is the daily savings for each project is just getting added together. So as more projects get completed, the daily savings rate increases. All right, so at this point, we've now talked through energy intensity models and project-based calculations. Let's do a little bit of review of some of the kind of limitations and advantages of each method. So the energy intensity model really is a comprehensive view of energy performance at your facility. We're going to pull in your facility-wide electric data. We're going to pull in facility-wide production data. We're going to consider weather. We're going to consider the operating schedule. And that allows us to look at really comprehensively the energy performance of your facility. Project-based calculations is a very different perspective on this. In this case, we're going to zoom way in to specific projects. And we're going to look at that project that you completed. We're going to get some equipment level or system level data so we can calculate the impact of that discrete project. We'll do that for the largest kind of projects you completed in the SEM program and add those all together as a way to estimate the impact of your SEM program. When thinking about the energy intensity model, it does have kind of a limitation in that it is sensitive to operational change. So energy intensity models, what they do is they rely on energy use patterns from the baseline period, and they kind of forecast that into your SEM program. So if you're in the SEM program and you have a big change to your operating schedule, to the product mix, or even your production rate, if you double the production rate in your facility, that's going to throw off the accuracy of the energy intensity model. And we often will see customers going through the SEM program who might start with an energy intensity model, and then partway through the SEM engagement, they have one of those big changes and it throws off the accuracy and energy intensity model, and then they switch over to project-based calculations because of that. Now, project-based calculations are less sensitive to these operational changes. So if you do, completely change your operating schedule or start running new product, again, we can more easily account for that with project-based calculations. So an energy intensity model is really best for sites with relatively stable operations and products. Bottom-up calculations work really well for sites with really fluid operations or where products are coming in and coming out and you're running different products every year. However, both of these methods are valid ways to quantify energy savings in the SEM program. And with both of them, we're going to give you some visual tools to kind of see your progress as you go through your SEM journey. All right, so with that, we have reached the end of Module 2. So as a quick reminder, Module 1 is where we provide an introduction to energy tracking and KPIs. In this module, number 2, we got into a little bit more detail on the different methods for energy tracking. And then module number 3 is where we're going to have this really deep dive into the energy intensity model. And that's going to be optional if you're going to be using project-based calculations, you kind of know that earlier on. This is going to be an optional module for you. However, if you are going to be getting an energy intensity model, we do recommend watching this video because it really will provide some key insights into how that energy intensity model is built, how to maintain that energy intensity model, and how to interpret the results. With that, I would invite those of you to complete the simple quiz and short evaluation. Your candid feedback is really helpful for us as it helps us inform future workshops and make sure we're delivering this in a way that is meaningful and impactful for you all. And by doing so, you'll get entered in for a raffle at the end with prizes. So thank you so much for watching Module 2.
Thank you all.